Okay, so here we are in Chapter 5, and we're going to be discussing how you figure out what the shape and polarity of a molecule is. And the first sort of application of this that's pretty relevant for most of us is how do people go about designing flu vaccines? And specifically, how do we anticipate what sort of vaccine that we'll need for a coming flu season? So one of the ways that it's looked at is we guess, pretty much. We draw statistical analysis and guess based on what kinds of flu we've had as to what will be big players in the coming flu season. And so we look at the antibodies that are in current use. When we look at the antibodies in current use, it turns out that the way that we've developed them, biochemists essentially, is to target a specific protein on a virus's surface. So what's interesting about this is that that region that the antibody is targeting, so the antibody is essentially your immune system's defense against this, can easily contort to a new configuration that's not blocked by the antibody. So it's a moving target. And one way to think about this is if you have your, if you hold up your arm and you have from your elbow to your wrist and then from your wrist to your fingertips. So your fingers can move around. So go ahead and make a fist. What they're saying here is that the antibody is essentially targeting your knuckles, okay, and on your fist. And if the antibody works because it can come in and block your knuckles, okay, and that blocks the flu virus from replicating or from entering host cells. We don't know exactly what happens. But if you think about it, what can your hand do? Well, you could straighten all of your fingers out, in which case then the bent area where your knuckle was is gone. You still have knuckles, but now they're in a different conformation. So this is what flu viruses do. They change their conformation. Now notice if the entire virus is from your elbow to your fingertips, that the flexible area is essentially your hand and your fingers, right? Those you can move into all sorts of different conformations. But from your wrist to your elbow, that area doesn't change much, right? It's pretty much just straight up and down. Well, what we've found is that recent research has found a group of antibodies that target that region, so that, and the analogy here is from your wrist to your elbow. They target a region of the virus that's right in there, so it's not able to contort and change its shape, so the antibodies can continue to attack it. What's really interesting about this, and you can read this article that I've got highlighted here if you're interested, is that the other issue with flu vaccines is that there are so many different variations of the flu out there. And so ideally you'd want a vaccine that addressed more than just one, because if you had to have a specific antibody for every single flu virus, you have a lot of antibodies that you're trying to design. If instead you could discover an area of the flu virus that's conserved across varieties and design an antibody to interact with that, then you'd be in pretty good position. So it turns out, back to your elbow wrist area, that area, which doesn't contort easily, is also conserved across different varieties of avian flu. And this article looks at some of that, and you can see the structure and what they're sort of thinking about. But the bigger picture for us here in Chemistry 121 is, what does this mean in terms of drug design? And how do researchers design drugs so that they're actually effective? And a lot of what it comes down to, just like here in the flu vaccine that we've been talking about, is shape. So, oops, this was going to be me drawing a picture of your elbow and your wrist, but I think you probably have a pretty good idea what that looks like. So, molecular shape. What does a molecule look like in 3 dimensions? It's, like I said, very important in drug design and biochemical processes. There's a lot of just the basic idea being you have a puzzle piece and you have another puzzle piece that fits together, and that those shapes have a particular way of interlocking that works for a lot of our biochemical processes, and thus then works for how we design drugs. Turns out you, in Chemistry 121, can determine the molecular shape using something called a Lewis dot structure and some knowledge of the valence shell electron pair repulsion model. So let's talk about those valence shell electron pair repulsion, which is often abbreviated VSEPR, up here, VSEPR, valence shell electron pair repulsion. So the basic idea of this is that electrons repel each other. And if you think about it, that kind of makes sense because electrons, one electron and another electron, both have the same charge. And we know that like charges repel. Turns out that non-bonding electrons, electrons that are not involved in a bond between two atoms, repel more strongly than electrons that are involved in a bond. And the reason for that is if you think about it, two electrons that are shared in a bond are shared between two nuclei, which means that they're distributed between those two nuclei and stabilized by them. But two electrons that are not shared in the bond, so they're just sitting alone on an atom, they take up more space, so they have more of a repulsion. The other big key idea here is that electrons, either bonding or non-bonding, because of the fact that they repel each other, will arrange themselves on the central atom so that they minimize that repulsion, right? It's just like when you think about if you go into a cafeteria to have lunch, you kind of sit with the people that you like. You try and avoid the people that you don't like. You're trying to maximize your repulsion energy from them. Same idea with electrons. So, how to draw a Lewis dot structure comes down to pretty much about 5 steps. First step, and before you panic with this long list, we are actually going to go through this process multiple times. So let's just get sort of a basic idea and then we'll apply it. So the first thing you're going to do is sum all the valence electrons for atoms in the molecule. And if you'll recall from chapter 3, the valence electrons, those are your outermost electrons. So if we had done, say, the electron configuration for phosphorus using the noble gas shortcut, it would have been, just for a demonstration here, would have been Ne in brackets, and then phosphorus, 3s2 and 3p3. S2, 3p3. So the valence electrons for phosphorus are those in the outermost shell. When we look at the electron configuration, we can see that the outermost shell for phosphorus is shell number 3. So that means that the number of electrons, the number of valence electrons that phosphorus has is 5. So it has 5 outermost electrons. So that's just a review of how we figure out valence electrons. Second, we're going to choose a central atom. It may be the atom that's written first in the formula. It definitely has to have the ability to make the bonds that are needed. It's generally less electronegative, and we'll talk about electronegative means before the end of this lecture. Carbon, if it's a choice, is going to be your central atom. Hydrogen and helium are never central because they're only capable of making one bond. Step 3, we'll place 2 electrons for each bond. These are covalent molecules, so we're having our bond is made out of 2 shared electrons. We're going to place the other electrons around the outer atoms until they reach a full octet, and we'll place the remaining electrons on the central atom if there's any remaining electrons to work with. So let's walk through this with PCl3. So I've totaled up the valence electrons. We have 5 from the phosphorus, and notice the chlorine, there are 3 chlorines. And if we figure out chlorine's electron configuration, it was neon 3s2, 3p5, which means that I have outermost shell is again number 3. Here's my shell number. And my total number of electrons in that shell, in shell number 3, is 2 plus 5. So that means I have 7 valence electrons. Whoa, it just took away my stuff. 7 valence electrons in each chlorine. So that's why we have 3 for the fact we have 3 chlorines, and each one has 7 valence electrons. So my total number of valence electrons then is all those things added together, and that gives me a grand total of 26. My central atom, if we go back and look at our list again, our central atom could have been written first, definitely needed to be able to make the bonds, and generally was less electronegative, and carbon is often central. Hydrogen and helium are never central. So, based on this, we're dealing with PCl3. You can see that phosphorus is written first. So that would make it a good choice. It's also a single element of that type, so that also makes it a good choice. And then when we think about it, phosphorus, we have that electron configuration right up here, needs access to 8 total electrons. Well, right now it only has 5. So if we think about each bond being something that gives phosphorus access to an electron, then phosphorus needs 3 more electrons, which means it's probably going to need to make at least 3 bonds. So when we look at this formula, if phosphorus was our central atom, it would have 3 chlorines attached to it, which means that phosphorus would need to make 3 bonds. And we've just checked the fact that phosphorus is indeed capable of making those 3 bonds. Chlorine is tricky. Sometimes it will behave sort of as expected, and sometimes it won't. So we're going to talk about its sort of traditional behavior and then leave the exceptions for a later discussion. Chlorine, we just did its Lewis dot structure up here. We saw that it had 7 valence electrons. It needs access to 8, which means that chlorine will probably only make how many bonds? Well, just 1, because it really only needs access to 1 more electron. So if this molecule, PCl3, needs 3 bonds, and chlorine is really only probably going to make 1, chlorine doesn't make a very good central atom, because we need a central atom that's able to make all 3 bonds. So phosphorus makes a good central atom, which you can see here. You're probably like, and it said right there. So then, let's see if we see. Oops, no, we're going to do the whole thing here. So when I choose my central atom, I'm going to draw a preliminary structure with the central atom in the middle. And I'm going to imagine it in a box. And each side of the box is where I'm going to put other atoms if I need to, or non-bonding pairs of electrons. So that's my preliminary structure, and I'm going to erase my box so it doesn't get in my way. See if I can manage to erase this without taking out the phosphorus. Whew, that was close. And get rid of that. There we go. A little bit of that. Okay. So now I've got 26 electrons. I know that I'm going to put electrons into my, oops, I got to do a little bit more erasing. Apparently I missed something. Get rid of this guy. And that guy. Okay. Now we're ready. I need to put 2 electrons per bond. So I've got a bond between the phosphorus and the chlorine here. So I'm going to put 2 electrons represented as 2 dots. So Lewis dot structure, a dot equals an electron. Notice it's between 2 atoms, so these are bonding electrons. There's 2 more, there's 2 more. Now, I had 26 electrons, but I've used up 6. Notice, which leaves me with 20, notice that I'm not thinking about how many electrons phosphorus started with and how many electrons chlorine started with, and I'm not concerned about whether they make it back on the right element or not. I've essentially ripped off the electrons and considered them to be in this big pot of 26 electrons, and I'm putting them back on the molecule as I find that I need them. So now I've made the bonds. Now I need to add electrons to my outer atoms until they have access to 8 electrons. So I'm going to put 2 on each side, again imagining a box around. And now if you count, that chlorine, just grab my red pen here, that chlorine has access to all of these electrons, which is 8. Okay, finish my other chlorines. 2, 2, helps that my mouse doesn't get in the way. Another 2, 2, 2. See if we can squeeze those in. Yep, they fit. All right, so I was down to 20 electrons, and I've added 18 more to my structure, leaving me with 2 electrons left. Each of my chlorines, just like this one that I've highlighted in red, has access to 8 electrons. They don't need any more electrons. 8 is it. They're happy. Phosphorus, on the other hand, only has access to 6. And you can see that here. Phosphorus has access to 6 electrons. It needs access to 8. I have 2 electrons to give it, so my last 2 electrons will go on the phosphorus, right up here at the top of my missing side of my box. So at that point, I've used up all of my electrons, and everybody in the structure has access to 8. So I'm done. Looks good. Let's do another example. What if you don't have enough electrons for everybody to have access to 8? Let's consider HCN. The H, first thing we want to do is count valence electrons. The H has 1 valence electron. Carbon has 4 valence electrons, and nitrogen has 5 valence electrons. So remember, valence electrons are outermost shell electrons. So this gives me a grand total of 10 electrons. Next, I need to figure out who my central atom is. And if you go back and look, or maybe you took notes, or maybe you have your PowerPoint slides in front of you, which would be a great idea for this one, it tells you that your choices for central atoms are, it could be the one of which there's only one of, it could be the one that's listed first, or if carbon is present, carbon's a good bet. So we've got carbon. So therefore, the central atom is carbon, and we don't really need to think about it any more than that. So I'm going to put carbon in the middle. I'm going to imagine my box and put hydrogen and nitrogen on sides of the box. Now, I don't have to put hydrogen and nitrogen across from each other. I could have put hydrogen on another side of the box or nitrogen on another side of the box. It doesn't really matter. So I picked my central atom. I've got 10 electrons. My first electrons go to make bonds. So there's 2 electrons for that bond and 2 electrons for that bond. I've used up 4 electrons. I have 6 electrons left. Hydrogen at this point has access to 2 electrons. And you'll remember from hydrogen's electron configuration, it's 1s1. So hydrogen only needs 2 electrons total, right? Because it really wants to be like the nearest knowable gas, who is helium, who only has 2 electrons. So hydrogen has access to its 2 electrons. It's perfectly happy. So we're done with hydrogen. Nitrogen, on the other hand, only has access to 2. So I'm going to place my electrons on my outer atom, which would be nitrogen, which then causes me to have 0 electrons left. Well, this is interesting because when we look at it, nitrogen has 8 electrons, or access to 8 electrons. Carbon, however, has access to how many? Just 4. Everybody needs access to 8. So what do you think you can do about that? Well, let's go to our next slide. And you can see what we end up doing is moving some of the non-bonding electrons on nitrogen and asking it to bond with carbon. So we take these 2 and these 2, and we put them and we make 2 more bonds. So let's back up and do that without these lines, because a line is essentially a bond, and eventually you can do that. But for right now, let's look at it this way. Here's my nitrogen. There's my carbon. I'm going to take these 2 electrons and put them in here, and I'm going to take these 2 electrons and put them in here. And so I'll have H, 2 bonding electrons, and then I will have 6 electrons for the carbon and 2 electrons on the nitrogen. Now, if you look at this, it works out, right? Nitrogen still has access to 8 electrons. Now, carbon has access to 8 electrons too, and they're both happy. And I don't need to move any more electrons because everybody has access to 8. So let's do some more examples. What is the Lewis dot structure of each of the following? Given what we've talked about with these 2 examples, how about you hit pause and do the carbon dioxide. Ooh, hold on, don't hit pause yet. Let's do carbon dioxide and an ammonium ion together, and then you can do carbonate, CBr4, and arsenic tribromide. So carbon dioxide. First thing we want to start out with is obviously the formula, which is CO2. Oh, I'm in red. Go back to black. Think about who my central atom is. Carbon, there's only one of them, and it's carbon, so it makes a good choice. So there's my carbons, and I'm writing the oxygens nearby. I need the total valence electrons. Carbon has 4 valence electrons. Each oxygen has 6 valence electrons, and there are 2 of them. So that means I get 12 electrons from there for a grand total of 16 electrons. My electrons go first into bonds. So here's a pair, and here's a pair. That takes care of 4, leaves me with 12 electrons. Next, my electrons go into outermost atoms. So I look at this oxygen and I see 2, 4, 6, and 2, 4, 6, and that takes care of all my electrons. I have no electrons left. Let's check and see who's happy and who's not. Each oxygen has access to 8 electrons. The carbon, however, has access to only 4. So carbon doesn't have access to enough electrons. I don't have any more electrons to give it. So that means I'm going to ask one of the oxygens to share electrons. So what I could do then is redraw my structure here without the circles so they don't distract you. And I'm going to take a non-bonding pair of electrons on this oxygen and move them in. Does that take care of my problem? Well, now carbon has access to 6 electrons, so it's not really enough. At this point, I have 2 choices I could make, and in Chemistry 121, either choice is perfectly fine. I could say, okay, carbon needs access to 2 more electrons, so I'm going to take 2 from the other side and put them in which case then I will end up with this. Which is actually the correct structure for carbon dioxide. It's nice, it's symmetrical, we like it a lot. You might have thought, well, why do I have to take them from the other oxygen? Why not just take them from the oxygen that I had? In which case then you would have ended up with this structure, a triple bond on one side and a single bond on the other. Now, for Chemistry 121, that's a perfectly acceptable answer because there's some other things, some other factors that come into play about why this is actually correct. For long term, we'll be using this structure, but if on a test you gave me this, I can see how you would come up with that, and so I would accept that as correct. Carbonate. This is where things get interesting because the carbonate is actually an ion, right? It's CO3 with a -2 charge. And this -2 means we have to add 2 electrons to our total. So I'm going to, for my valence electrons. So carbon has 4 valence electrons. Each oxygen has 6, and there are 3 of them for 18. I'm going to add then all of these together, and that gives me a grand total of 24 electrons. Now, if for some reason this had actually been CO3 with a +2 charge, I actually would have had to have subtracted electrons. So I would have had 4 from carbon, 18 from the oxygen, and then I would have had to subtract 2, in which case then I only would have had 20 electrons to work with. So negative charge means we add 2, positive charge means we subtract however many the charge is. So we're dealing with carbonate, which has a -2 charge. We have 24 electrons. Carbon is our central atom. So there's carbon. Here's some oxygens going around it. I need to place electrons in my bonds first, which uses up 6 electrons. I have 18 electrons remaining. I'm going to place them around my outer atoms until each atom has access to 8. Notice I'm pairing them on the sides of the box. That's pretty much convention in terms of Lewis dot structures. And at that point, you'll see we've used up all of our electrons. But someone does not have access to 8. Carbon only has access to how many electrons? 6, which means that it needs access to 8. So I'm going to ask one of the oxygens to move a non-bonding pair of electrons into the bond. And it doesn't matter which oxygen I choose. So I'm just going to do this one, which then means that now my structure looks like this. And I'm going to start drawing straight lines to represent bonds. So I've got a C bonded to an O, and I've got a C bonded to an O down here. And then I've got a C with a double bond bonded to an O. Now my last step here is because this had a charge, because it's carbonate, I have to put brackets around the structure and put the charge on the outside, so that someone who comes behind me and looks at that structure knows, oh yeah, there are 2 extra electrons in there because this has a -2 charge. Okay, but you go ahead and do ASBR3 and, whoops, thought we had another one. I guess we just have ASBR3. So go ahead and hit pause and do the Lewis-Dot structure for ASBR3. Okay, so arsenic tribromide. Arsenic has 5 valence electrons. Each bromine has 7 valence electrons. There are 3 of them for a grand total of 21. You may have noticed at this point that we don't ever come up with an odd number of electrons. And that makes sense because either our atoms should have access to 2 electrons if they're hydrogen or helium, or they should have access to 8 electrons if they're everybody else, which gives you even numbers. So if you come up with an odd number of electrons, then you want to go back and check your addition here and your number of valence electrons to make sure that you have those correct. Central atom is the one that's written first and which has the capability of making all 3 bonds that I need to make, which would be arsenic. And so I've got arsenic in the middle and then 3 bromines around the outside. And then I'm going to put electrons into my bonds first, which takes away 6 electrons, leaving me with 20. And electrons then on the outermost atoms, which takes away 18 more, leaving me with 2 electrons at the end. Arsenic, I notice, has access to 6 electrons. Each bromine has access to 8 electrons, so the remaining 2 electrons go on arsenic. And that's my final Lewis-Dot structure. Hopefully that's what you came up with. So, Lewis-Dot structures I promised you would help you figure out shape. So it turns out that the number of bonding and non-bonding electrons on the central atom will determine the shape. We'll start with the full shapes, meaning there's no non-bonding electrons. We'll go ahead and look at a, picture here. If I can get my slide to advance. If you have 2 bonds that are being made to your central atom and no non-bonding pairs of electrons, then you have what's called a linear shape. And in your textbook, it's helpful for you probably to reference the pictures of these, which I will actually be showing you as well here in just a second. You can get a heads up on where we're going and have this open as you're working, because it'll be a reference that you'll use pretty often. And what we're looking for here in Chapter 5 is a list of all the shapes. And you can find that on page 121. It's a table labeled the geometry of molecules. So if I have 2 bonds and no non-bonding electrons, it's linear. If I have 3 things bonded, so 3 single bonds, or 2 bonds and a double bond, or essentially that I have 3 things attached to my central atom and no non-bonding of electrons, that's trigonal planar. If I have 4 things bonded to my central atom and no non-bonding electrons, it's tetrahedral. So here's what those shapes look like. Linear, I've got two things attached to my central atom, and it's a nice straight line, has a 180-degree bond angle. When I move and have three things attached, now it's flat. I'm in a plane still. I've gone from a line to a plane, geometry there. And my bond angle now is 120 degrees, right? Still minimizing the repulsion, maximizing the space between bonds that we see. When I add four things, what we have to remember here is that we're we're three-dimensional, which means when I add that fourth thing, it doesn't just add in the plane, it adds out of the plane, and I actually get a tetrahedral shape with a bond angle of 109.5. If I were to add yet another thing, 5 things, I'd be trigonal, bipyramidal, and 6 would be octahedral. Now, in Chemistry 121, we don't really look at trigonal, bipyramidal, or octahedral. Those are bigger, what are called expanded octet shapes. We're going to focus in on linear, trigonal, planar, and tetrahedral here. So, how would you figure out the shapes of the following? Well, essentially, you would be drawing a Lewis dot structure and then counting the number of things that are attached to your central atom and the number of non-bonding pairs on your central atom. Notice we're just interested in the central atom. So carbon dioxide, let's see if I have oh, I do. Carbon dioxide, let me get all those. Carbon dioxide, CCl4, and nitrate. So CO2, CCl4, and nitrate, which is NO3, -1. And the question is, what is the shape of each of these? Well, if you'll recall, we already did the Lewis dot structure for carbon dioxide, and it looked like this. So when we look at our central atom, we can see it has two things attached to it and no non-bonding pairs of electrons on the central atom, which means that this fits with linear. CCl4, to do the Lewis dot structure, how about you take a moment and do that? Hit pause. Okay, so we're back. CCl4, carbon has 4 electrons. Each chlorine has 7 electrons. There are 4 of them, for a grand total of 32 electrons. Central atom, carbon, good choice. And I'm going to have 4 bonds attached to the chlorines coming out from the carbon. And each of the chlorines has a full octet of non-bonding and bonding electrons. So in terms of deciding shape, though, I'm just looking at the central atom, which is carbon. And we see that it has 4 things attached to it and no non-bonding pairs of electrons, which means that the shape of this atom, this molecule, is tetrahedral. The nitrate ion, go ahead and do that Lewis dot structure. Hit pause. So nitrate, we have nitrogen with 5 valence electrons, each oxygen with 6 valence electrons. There are 3 of them. And I have to add that extra electron because of the charge on the nitrate, which gives me a grand total of 24 electrons. Nitrogen is my central atom. It's both capable of making the bonds, and there's only one of them, and it's written first. So nitrogen, oxygen, oxygen, oxygen. Put in my bonds. Put in my electrons. And what we'll find here is that my last 2 electrons actually end up getting shared. Sorry, it's not the greatest. That's actually 4 electrons there. And making a double bond with the nitrogen. Last step is to put it in brackets, pop the charge out there. So in terms of my shape analysis, I'm just looking at the nitrogen. It's got 3 things attached to it. Now, one of those is with a double bond. We're not so interested in that. We're interested in the fact that it's got 3 things attached to it and that the nitrogen has no non-bonding pairs of electrons on it. That means that this shape of this molecule is trigonal planar. And there they are. So what happens if some of the bonding electrons get replaced with non-bonding electrons? Well, we get a whole slew of other shapes. If we start with tetrahedral and take one pair of electrons away, one bonding thing away, and replace it with a pair of non-bonding electrons, then our shape is trigonal pyramidal. If we take a second bonding thing away and replace it with a non-bonding pair of electrons, now we're looking at bent. Every time you replace electrons with non-bonding electrons, it changes the shape, and it also changes the bond angle. Because if you'll recall, our non-bonding pairs of electrons take up more space than bonding pairs of electrons. So the effect there is that we see that the bond angle in tetrahedral was 109.5. But in NH3, where we've got that non-bonding pair of electrons, now that bond angle is shrunk a little bit to 107. And if we go to water, which now has two pairs of non-bonding electrons, the angle shrinks even more to 104.5. Why do those bond angles change? Well, remember we talked about the fact that your bonding electron pair was between two nuclei. And so that sort of evened out your electron density. But in a non-bonding pair of electrons, it takes up a huge amount of space, which means that it's going to take up that space and its repulsion force is going to be greater than the bonding electrons. Multiple bonds, so a double or a triple bond, have a slightly smaller but similar effect on shape as well. So, what are the shapes of the substances below? Let's see if I have slides. I do. So XeO3, pH2, -1, and my last one was GeBr4. EBr4. So since we've done some examples together, I think this is a good opportunity for you to do these by your own first and sort of assess, are you understanding this material or are you still kind of confused about some things? So go ahead and hit pause, do each of the Lewis-Strauss structures and decide the shape of each, and then we'll come back together. And it'd be helpful to have your textbook open to page 121 so that you can determine the shape. Okay, so you should have Lewis-Strauss structures in front of you and shapes that you've thought about. So Lewis-Strauss structure for XeO3, xenon brings 8 electrons to the table, and each oxygen brings 6 times 3, which is 18, for a grand total of 26 electrons. Xenon is my central atom. And the reason for that is it's written first, and there's only one of it. So I've got xenon, I've got each oxygen, and I'll find that I have a bond to each oxygen, and then each oxygen has access to 8 total electrons. And that will have used up 24 electrons. And that will leave me with 2 left, and they will go on the xenon. So when I look at my central atom, I see that it has 3 bonds and 1 non-bonding pair of electrons. And if you check page 121, you'll see that 3 bonding and 1 non-bonding leads you to trigonal pyramidal. So the shape is trigonal pyramidal. pH2 -1, phosphorus has 5 electrons. Each hydrogen brings 1, and there are 2 of them. And then I have that -1 charge, which means I have to add an extra 1, which gives me 8 electrons to work with. Phosphorus is my central atom. It's single, it's written first, and hydrogen is not capable of making enough bonds. Hydrogen will only make 1 bond. So I end up with the phosphorus connected to the 2 hydrogens, and then I have extra electrons sitting on the phosphorus. So when we evaluate our central atom, we see it has 2 pairs of non-bonding electrons, 1 here, 1 here, and 2 bonds. So 2 non-bonding pairs of electrons and 2 bonds gives me angular or bent. You can call it either. Textbook calls it angular. I tend to call them bent, but they're both acceptable. Germanium tetrabromide. Germanium has 4 electrons. Each bromine has 7, which gives me a grand total of 32 electrons. So germanium goes in the middle. The bromines go around each side. Bromines all have access to 8 electrons, as does the germanium, and my Lewis-Dot structure is complete. To figure out shape, I look at my central atom and see it's got 4 things bonded to it, which means that this shape is tetrahedral. So, just to run through that again, XeO3 had 1 non-bonding or 1 lone pair of electrons and 3 bonding pairs, which made it trigonal pyramidal. pH2-1 had 2 non-bonding or 2 lone pairs of electrons and 2 bonding pairs, which made it bent. And GeBr4 had no non-bonding or lone pairs of electrons, 4 bonding pairs, which made it tetrahedral. So then the question becomes, are the electrons shared equally? If we think about it, we have H2, which looks like this. Or better yet, let's draw it this way. Here's my pair of electrons. And we also have NH3, which will look like this. And the question I'm asking is, do you think in H2 that the electrons are shared equally? Why or why not? And do you think in the NH bond and NH3, I'm talking about these guys right here, are shared equally? Why or why not? So take a moment, hit pause, think about that. Well, one thing we know is that how much an electron or a pair of electrons is attracted to a particular atom has to do something to do with its number of protons, right? Because electrons we know are attracted to protons. So in H2, we have 1 proton over here and an identical proton over here. So therefore, the electrons are shared equally. So this has equally shared electrons. That means that this is what we call a non-polar bond. In NH3, however, nitrogen has a heck of a lot more protons than hydrogen. There's a little bit more going on with it than that, but let's stay with that for right now. That means that if we isolate that nitrogen-hydrogen bond, if we were to draw where those electrons were, they're mostly hanging out close to the nitrogen. Now, we know that we can just talk about the probability of where electrons are. So some of the time, they still are being accessed by hydrogen, or else there wouldn't be a bond. But because they're mostly over there with the nitrogen, hydrogen's nucleus looks a little bit naked. It's a little bit exposed, which means that we start to build up what is called partial positive charge. And this funny symbol that I just drew here is called a lowercase delta, and it just means partial in this application. And I've drawn the positive here to show that I'm building up a partial positive charge. It's not a full positive charge because I'm not making an ion. This is still a covalent compound. It's between 2 nonmetals. Yes, hydrogen is a nonmetal. Nitrogen, on the other hand, has more electrons, right? It's got those electrons it's supposed to be sharing with hydrogen actually snuggle up pretty close to it most of the time, which means nitrogen is looking pretty electron rich, which means we've got that partial positive there on hydrogen, and we build up a partial negative on nitrogen. This is called a polar bond. The electrons are not shared equally. And so I build up this partial positive charge here and here. And this just looks at what we just talked about and why. So, broader definition of why this happens is called electronegativity. And that is basically the ability of an atom to attract shared electrons in a bond towards itself. And there's trends in electronegativity. Turns out that if you look at a particular row on the periodic table, the electronegativity increases from left to right across a row. And it also increases as you go up a column. So in your textbook, you have a table of electronegativities. And you can see here, if we look at the second row, that as you go left to right, your electronegativity values are increasing. as you go up a column, your electronegativity values are increasing. So do you have to memorize these individual numbers that denote electronegativities here? No, you don't. But you do need to remember that on the periodic table, the trend is increasing as you go across and increasing as you go up a column. So polar bonds then, we can now incorporate this new vocabulary, are formed between two atoms. Oh, whoops. Got ahead of myself there. A nonpolar bond is formed between two atoms with the same or similar electronegativities. So for example, in a sulfur-sulfur bond, I've got two sulfurs, they have equal electronegativity. We know those electrons are shared equally. The other example that you want to be aware of that you wouldn't think of necessarily, but we know that this is the way it is that the CH bond, any carbon-hydrogen bonds out there, are nonpolar as well. If, on the other hand, you have a bond formed between two atoms with a difference in electronegativity, then that's a polar bond. One atom has a greater ability to attract shared electrons towards itself than the other, so the electrons are hanging out closer to that atom than to the other one, and so we start to build up partial positives and partial negatives. What does this look like? Well, in terms of electron densities, we can look at, for instance, F2 here, and see that essentially I've got a fluorine atom here and a fluorine atom here, and my electron density is evenly distributed because both of them have the same electronegativity. If, however, I replace one of those fluorines with a hydrogen, hydrogen has a vastly different electronegativity than fluorine, now we start to see some difference in electronegativities building up, and so a difference in how the electrons are shared. And this red is showing me that, and we can also just see in terms of size, I'm getting a bigger size out here and a smaller size out here. My electron density has moved this direction. So I've got a partial negative on the more electronegative element, which is fluorine, and a partial positive building up on little old hydrogen. In lithium fluoride, now I'm not even in a covalent compound. I've got a metal and a nonmetal. So these are fully ions. I've got a lithium +1 cation and a fluoride anion. So we've got fully positive here and fully negative. So that's definitely polar. How can you decide whether a molecule is polar? We've talked about how to decide whether bonds are polar based on these electronegativities, but how do you decide going from just a single bond to the whole molecule whether it's polar? Well, draw a Lewis dot structure and then look at that arrangement of atoms and bonds and non-bonding electrons. Molecules that are symmetrical will be nonpolar, while molecules that are not symmetrical will be polar. Let's look at some examples. For instance, here I've got H and I've got Cl, right? This is actually just a bond, different electronegativities. Chlorine is more electronegative than hydrogen, so it's they're showing the dipole moment here where the positive end's on the hydrogen and the negative end's sitting on the chlorine. Let's go ahead and look here at a tetrahedral compound though. Carbon's in the middle. It's got 4 equivalent chlorine bonds going in 4 different directions. Turns out each of those bonds is polar, but guess what? Each of these dipoles, they cancel each other. So overall, the compound as a whole is symmetrical, and because it's symmetrical and the fact that the dipoles cancel, this is a nonpolar compound. If we look at ammonia, NH3, you can see that up here there would have been 2 non-bonding pairs of electrons. So this is not a symmetrical molecule. It's got non-bonding pair of electrons up here and 3 hydrogen bonds going on down here. Not the same things on the central atom. 1 non-bonding pair of electrons, 3 hydrogen atoms bonded. So definitely not symmetrical, definitely polar. Check out this CH3Cl. 3 CH bonds, 1 CCl bond. 4 things are not the same all around the carbon, so it's not symmetrical, so this molecule is polar as well. Over here on BF3, we're actually looking at a trigonal planar molecule. And because it's flat, we see that there are 3 of the same things attached to the boron, all fluorines. So the equivalent electronegativity and equivalent polarity of each of those bonds ends up canceling each other out because it's symmetrical, and so this is a nonpolar molecule as well. So back to our examples. Are the following compounds polar or nonpolar? And for the sake of practice, you'll want to go through this and do the Lewis-Dot structure and look at the shape and then decide whether it's polar or nonpolar. So go ahead and hit pause and engage in that. Okay, so carbon dioxide we've drawn a couple of times already today. Oops, if I can get my electrons to show up there. And we see that carbon dioxide, the carbon has two of the same things attached to it. It's linear. The oxygens are pulling in equal and opposite directions, the electronegativities, which means that they cancel out. Cancel. Which means that this is a nonpolar molecule. Does it have polar bonds? Yeah. But overall, they cancel each other. So the molecule is nonpolar. NES3, neon, has 8 valence electrons plus 6 from each sulfur, of which there are 3 of, which gives me 26 electrons. That's going to give me this shape. Where I have 3 things bonded to the neon and 1 non-bonding pair of electrons sitting up there. And so that means I have 1 thing of one type and 3 things of a different type bonded, attached to the neon, which means that this is not a symmetrical molecule, which means that it is polar. One nice thing to pick up here is that trigonal pyramidal molecules will always be polar because they will always have a non-bonding pair of electrons, which will always cause them to be not symmetrical. H2SE actually looks like this when you draw it, but we have to think about its actual 3-dimensional shape here, which is bent. Turns out both of those non-bonding pairs of electrons are on the same side, which means that although it might look symmetrical when we draw it this way, when we think about its 3-dimensional shape, we can tell that it's not symmetrical. And so this is polar. This again, if you think about it, all bent molecules will be polar. CHF3, I've got carbon in the middle, H, each of the F's in my tetrahedron. We can see that you've got 1 hydrogen and 3 fluorines. So 2 different types of things attached to the central atom means it's not a symmetrical molecule, which means that this molecule is polar. Oh, where's my answer slide? So that's it for Chapter 5. The homework problems that you'll want to look at are 1 through 18 and 23 through 60.